blow the roof off. I've been pedaling here a while, and I'm just about out of energy. That's what we're going to explore today, energy and where it comes from. Whoa, I feel like I've used up a lot of the energy my muscles had stored up as glycogen, and I need more. I'm going to make a quick run to the grocery store, and then track down Ed.
Just watching TJ do all that work makes my fins hurt.
Yeah, man. She used up a lot of energy.
I'm tired from watching her. So here's question 1. Where do Cephas and I get energy from?
Hi, TJ.
Hi, Ed. I've been looking for you.
I see you've been shopping.
Well, I ran out of energy while I was exercising, and I decided to go to the store and get more.
So there's a store where you can buy energy? Just buy energy?
Not really. I did buy this stuff, but the grocery store isn't really where energy comes from. Like these apples. They get their energy from the leaves, which in turn get their energy from the sun by a process called photosynthesis.
That's the same thing that gives us peanuts, isn't it?
Right.
You know, when we eat peanuts or apples or other food, we burn them inside our bodies, and it's that burning process releases energy that we use, and TJ uses when she goes exercising.
Right. Can we see how that works?
Sure, because we can actually burn a peanut. Let me get a candle started. When you're going to burn something, you need 3 things. Oxygen, which is in the air all around us. Of course, we breathe oxygen so our body can burn food. You need fuel, in this case it's a peanut, and we also need some heat. In this case, I'm using a candle. So we'll just heat the peanut up a little bit, and it's burning. TJ, how long do you think that peanut's going to burn?
A couple seconds.
Okay, you just watch that for a second. There's a heck of a lot of energy in a peanut.
It's been more than a couple seconds.
It has already, indeed.
Well, you know, I also bought some peanut butter. Peanuts not only give off energy, but it takes energy to change a peanut into peanut butter. Do you think we can trace the path of that energy to its source?
That's a gnarly idea, TJ, and I know we can because we can start with this electric blender or grinder, which is used to grind up the peanuts, and we know it gets its energy from the electric cord, and it gets its energy from the extension cord, and that's plugged into the wall right over there. So I think the energy for the peanut butter comes from the wall.
Do you suppose it comes into the wall through electric wires hooked into electric lines that hook into an electric company?
Well, every month you get an electric bill at home for the electricity you use, so you might think there's an electricity store just because you bought some.
But is there an electricity store? We trace the path of electricity to the illuminating company and beyond.
Hi, we're at the Perry Nuclear Power Plant finding out where some of the electricity that you use, in fact, maybe powering the television you're using right now in your classroom, where that comes from. Linda, the tall towers behind us, that must be where all the electrical energy is generated.
No, Ed, that's not where it comes from.
No! What are those tall towers for?
Those tall towers are called the cooling towers, and they're like big radiators that are used to cool some of the water used throughout the plant. It's important to know that that water in the cooling towers never comes in contact with radioactive material. It's just a real environmentally friendly way to return water to the lake, and it's used for many other types of plants, like coal plants as well.
That's right. For really large coal-fired plants, you see the same sort of towers. But if that's not where the electricity comes from, we saw the wires coming in. Where is electricity generated here at the Perry Nuclear Power Plant?
Well, the electricity comes from big electrical generators, the same type of generators that you would find in a coal plant or an oil plant or even in your automobile.
Okay, now the generator is turning, and it turns within a magnetic field, and that generates electricity, but something has to turn the generator. What provides the energy to turn that generator?
Well, the generator is attached to a turbine, and a turbine consists of a big machine with a lot of blades, like a child's pinwheel blades.
Or a fan that you're blowing wind through and driving it backwards.
That's right, but in this case, the driving force is steam.
Steam. So we've got steam turning the blades of the turbine, and that turns the generator, and the generator generates electricity, and that goes out on the wires. But what generates the steam? To make steam, we have to have heat.
Well, the steam comes from boiling water in the nuclear reactor.
Okay, so everything up to this point is exactly the same, regardless of whether it is a coal-fired plant or oil or gas or nuclear.
The only difference, really, in the whole process is what kind of energy you use to boil that water and produce the steam. In this case, you use nuclear energy, which goes back to using uranium as a fuel.
Okay, and in all those processes, you have to control them because they're pretty immense processes. You've got pipes going everywhere, heating pipes and cooling pipes and turbine speeds. So you have to control that in some sort of a central place.
And most of the control, centralized location in the plant, or the brains of the plant, is our plant's control room. This is where you can control the nuclear processes as well as a lot of the cooling water types of processes that go on in the plant.
So just think about it. The electricity you're using right now or when you go home this evening either came from our sun, which made coal, oil, and natural gas many millions of years ago, or it came from a nuclear power plant, in which case the energy source was uranium, and uranium came from a star that exploded 4 or 5 billion years ago. So in either case, it came from a star. That's kind of neat. Think about that when you turn something on. Thanks very much, Linda.
Thank you, Ed.
Oh, hi, TJ.
Hi.
You know, TJ, as I do more activities, I learn a lot more about where energy comes from.
Well, I see you have some potential forms of energy. What are you doing with them?
TJ, I'm trying to make a turbine, just like the electric power company uses when they generate electricity. So I have cut these. In fact, would you cut one more slot here and bend it up just like these? Students, here's something you could try at home, taking a piece of manila cardboard, cutting a circle out, and then cutting some slots in from the edge and bending them up as in the vanes of a windmill or a turbine, and then supporting the whole thing with a string. So we're ready to give this a try. Here we've got a candle which is heating the air, and as the air rises, it comes up and pushes up through the blades of the turbine and pushes it around.
I see it turning.
Yeah, it didn't work very well, but it did turn a little bit, didn't it?
Well, what if we wanted it to move faster?
We could cut more slots and put more vanes into our turbine.
Or what if we cut them in farther in the center, farther towards the center? Or what if we bent these up farther up or farther down?
Well, that might work to cut them in farther and certainly might work to change the angle. And I'm not sure what the optimum conditions are, but we could have lots of fun doing experiments to find out. The other thing we could do is instead of using warm air rising, we could use steam rising. We've got a hot plate here, and it's boiling water, and the steam is coming up. And let's see what happens over here.
Okay.
Let me get this right.
Oh, look at that. It's turning even faster.
Yeah, it's turning a little bit better, isn't it?
Right. Now, what if you move the turbine closer to the steam or farther away from the steam? Would that make a difference?
I think it would, TJ. I think it might work a little bit better if it were closer. But the other thing we could do would be to enclose this area in a tube and capture all that steam and force it to rise up. That's what they do at the electric power plant when they're generating electricity. They have a closed system, so there's no other air currents flowing through there, and so the steam can't escape. Now, if we did that, this turbine would really spin fast.
So a lot more work can be accomplished when the steam is not interrupted by another airflow. Based on that knowledge, someone must have said, what if we made that a closed system? And the results have been fantastic. We have lots more energizing ideas to show you.
TJ and I are out in the woods, and we're going to build a little fire. We've got some wood here, and the wood has a lot of energy inside of it, but we have to release that energy somehow to make a fire. You know, a fire needs three things. It needs fuel, and we've got that. It needs oxygen, and we've got lots in the air around us, and it needs a third thing, and that's heat. So we have to figure out how to generate enough heat to get the wood started, TJ.
How are we going to do that?
Well, typically you think of doing it with a match, and you just get the match started and you start burning something small, and that burns the wood.
Right.
But that would be too simple, wouldn't it? We don't want to do that.
I guess so.
We could use a magnifying glass. It's a nice sunny day. We could magnify the sun's energy on a little tiny spot, and this will hurt very quickly, like now. We could put some dried grass there and get that burning. So that would be one way of doing it.
Right.
We could use a little bit of flint and steel and make some sparks into a dry area.
Oh, wow.
And that would get us started pretty quickly. That's very reliable.
That's neat.
Here's another method. This is a friction fire method. And all we're going to do, TJ, that's for you. And this is just to hold it in place at the top. And we're just going to spin this back and forth. And you watch down here very quickly where the dried grass is, and you'll see in just a matter of a few seconds that a little harder there, TJ.
Okay.
Okay, we're going. See how long it takes us to get some smoke going. How we doing?
Well, I can smell something.
A little more. There's the smoke coming up. TJ, I think we're getting somewhere.
Look, there's some smoke there.
Yeah, let's stop here. This method works really well because the hardwood of the spindle rubs against the softwood of the base, and as it rubs faster and faster, it causes a lot of heat due to friction, and that heat eventually will ignite the dried grass, and from there we can use that to ignite the wood. So we can release the energy that's in the wood by applying some heat from a number of different methods, including the friction method.
But where does the wood get its energy to begin with?
That's a good question, TJ. In fact, let's use that for question number 2. Students, where does the energy come from that's in the wood, the energy that we're going to release in a fire? You know, when you're out cruising around in your car, eventually you have to stop and get some more gasoline. So here we are at an energy store getting some gasoline, some energy for TJ's car.
But is this really an energy store?
Sure, TJ, this is where you buy energy. You pump it out from the pumps into your car so your car has lots of energy to go.
Yeah, but that gasoline has to come from someplace.
It does. It comes from a giant tank underground, and you're pumping it right now up through this pump into your car so you'll have energy.
All right, where does the tank get the gasoline?
The crude oil originally formed as plants, and as the plants fell down as they died and were compressed and laid over with other sediments, eventually that material, that plant material, was converted to oil and gas. And that's the material that's in the ground in Alaska that's pumped out, put into the pipeline, put into the ship, that goes to the refinery, that goes to the tank truck, that comes and puts it in the tank here, that goes into your car.
Wow. So let me get this straight. The crude oil is made from dead plants which get their energy from the sun.
From the sun. That's right.
Okay, well, now that we've got the sun's energy in the form of gasoline, let's go cruising.
Okay, TJ.
This car sure has a lot of energy. Where does it come from?
TJ, if we look in this compartment underneath, we'll find a whole bunch of batteries.
So you might think that you buy the energy from the store. Well, you do buy the batteries at the store, but the batteries have to get their energy from someplace. I'd like to know where. Wouldn't you?
I sure would, TJ. I bet you the people at Everready can help us out.
We've been talking about energy and where it comes from. We're here at Everready's Research Center in Westlake. Dan, where does the energy come from to make a battery?
Well, I'll tell you what, why don't we make a battery, and as we make a battery, we'll see.
Okay.
One of the materials that we use in a battery starts off with manganese dioxide. This material is mined all over the world. We get it from Brazil, we get it from China, Africa, a number of places. That material is ground up into a fine black powder that goes into the battery. The other material we have is zinc. This material was mined in Philadelphia. This material is melted down, impurities removed, and a callet is formed. From this callet, we then extrude a can.
Now, extrude means you draw it or you push out on this little piece to make the cylinder that becomes the outside of the battery.
That's right. Now, with that outside of the zinc can, we then add a separator. We have a little bit of water that we put into this battery, and then we take and we tap in the manganese dioxide. We then pack it down so that we push the chemicals out close to each other so that the reactions occur.
So we get a good reaction.
And we continue to put more of this in, and we pack it way down.
Now, Dan, what we're going to end up with here, you're going to keep pouring the manganese dioxide in there, and we're going to end up with a chemical reaction occurring between the zinc and the manganese dioxide. Those two materials are going to change chemically, and as they change, they will let electrons loose, and that flow of electrons will give us electricity.
That's right. That's
Okay.
how we produce it.
Now, you have one other piece here.
One other piece, the carbon rod, goes into the middle of the battery, and that's so that we can put or have a path for the electrons to flow.
So that's like a conductor?
This is like a conductor
Okay.
for the electrons. Now we've, in essence, made a battery. That battery is very similar to one of these batteries.
And we've made a D-cell battery.
That's right.
Great.
And there's such things as C and AA. How come there's no B batteries?
Well, there is a B battery. It's just not a common battery in the United States. At our French plant, we do make B batteries. There are actually 3 B batteries that go into this light. This light is commonly used in bicycles over in Europe. It's just not a popular size in the United States.
Great. Dan, can we see if our battery lights up?
Sure.
Can I
Go
try
ahead,
it?
try it.
Go ahead, TJ.
Thanks. Okay. Just put this here.
Yep.
and it
Flip it
lights
on.
up.
Wow, that's neat. We just made a battery. You
That's
gave
all
us a
there is.
charge.
Yeah. Well, thanks. We've had lots of fun.
Thank you for coming.
Thanks, Dan.
We are surrounded by dead batteries. Al, what makes a battery dead in the first place?
Well, these batteries here are used in big industrial equipment, and as they're being used, all the energy's drained out of it.
How do you put energy back into the battery?
We hook them to the battery chargers there, and they put the voltage back into the battery.
When you recharge the battery, what exactly is happening inside the battery?
There's a chemical reaction takes place in the battery. The voltage coming through the cables and the amperage charges the acid in the battery, which gives it its life.
Well, thank you for charging up our knowledge base. We've learned a lot about recycling energy.
Thank you.
Why do humans wear energy as clothes?
Don't know, man. Maybe because they don't have scales.
Here's question 3 for the students. Can you trace Ed's cotton shirt to its energy source?
What are you doing, Ed? Playing with toys again?
Yes. Well, no, TJ. I'm getting ready to demonstrate that wind is a form of energy.
But where does the wind come from?
Well, we can show that right here, TJ. We've
Okay.
got a bowl of very cold water and a bowl of very hot water. In fact, it's so hot I won't put my finger in. And we've got a couple bottles set up to simulate what happens in our Earth's atmosphere. This one was filled with smoke, so we'll be able to see the smoke travel. So let's put this one in the cold water and put that one in the hot water. And can you take off the tape there, and we'll plug this in. See a little bit of the smoke coming out there. Can you push a little bit?
I got
Good.
tape stuck
Okay.
in my hand.
And we'll take off the top. Now, because we have hot air on this side, TJ, what do you think is going to happen over here?
Well, I know that heat rises, so I think it'll rise.
Okay, so if this side rises and carries the smoke with it, and this side, what's going to happen over here?
Well, I think the air will sink, or the smoke will sink.
Because over here, the air is cool. So we have warm air rising, like it does at the equator, and we have cold air sinking, like it does at the pole, but we can't have all the air ending up at the pole, so we have to have a return circulation. That's the Earth circulation, and we call that wind.
I can see the smoke going through this tube, and it's slowly going down in there.
Okay, we'll take a few seconds, and then we'll see the smoke starting to go back the other direction.
Now, what if we switch the bottles? We put this bottle in here and this bottle here. What would happen?
Well, we would see if we did that the circulation would change because, again, we're heating one side and cooling the other. Just like a heat engine or a gasoline engine has to have a hot side and a cold side. The Earth's atmosphere is a giant heat engine, and the sun is its source.
We found out today that there really isn't an energy store. All energy comes from somewhere in our environment. All you scientists need to keep tracking what you use to the source of its energy so you can make better decisions about your world. Thanks for watching, and be sure to tell everybody that science is fun-tastic.